about 6 minutes before class starts. Anybody want some free math?
Free math?
Free math, no charge. I can just start going through problems in the book. There's no reason for me not to. I mean, it's not like we're going over a section of the book at this point. I'm going to start now. You're here. Oh, and Amy's here, so we can talk about your question. So let's start off with that. So, if this was a question from the quiz, one of these. And the question was something like this: let P be T is a linear transform. Let's try that again. T is the linear transformation that is the reflection across a line I'll put that in parentheses. 2, 2, 1. May not be the right numbers, but the ideas will be the same. Okay, so in pictures, it's not necessary to draw a picture in order to solve this, but in pictures what we've got is, say 1, 2, 1. Beautiful, beautiful drawing. So this is the vector 2, 1. And when I say the line 2, 1, what I really mean is the line that's determined by this vector. So this line right here. And if we have some point like this, then let's call this x. Then maybe like this would be t of x. So it flips it across that line. And the question has several parts. We want to figure out what, you might have to remind me exactly what the other parts of this question say. But we are given a basis, and then we do all of our calculations in that basis. So with respect to that basis. And the basis we're given is -1 and
-1, 2.
sorry?
-1, 2.
-1, 2. I was going to say 1, -2. Actually worse, either way. Oh, so let's say let B, we'll call it B, be a basis for R2. The fact that we're dealing with R2 is implicit in the fact that this is a R2 vector. This is a basis for R2, in fact. Actually, we can pretty easily check that this is an orthogonal basis. Right? The point of using this basis is that it's easy to see what the transformation does to this. So if we call this one B1, and this one B2, then what does T do to B1? It's just B1. And what does T do to B2? Well, okay, so why is this one? I didn't give any explanation for this. Why is this one? What's so obvious about this? Well, this 2, 1 is actually on the line. The T anything that's on the line, t sends it to itself. So, we get this. Now, in this case, what we have is negative 1, 2 is actually this vector. These are perpendicular. So the reflection across the line if this is, I'll write this as B2. And what this is negative B2. So we didn't have to do anything complicated in order to figure out what the what t did to these things. It's purely geometric, right? There's no computation involved. So this is minus B2. So how do we proceed from this? One thing that we could do is we could figure out what the matrix of the, what do they call this in the book? The B matrix. So if we think about R2. So T takes something in R2 and sends it to R2. If we look at an element with respect to the basis B, then we can think of each of these things as being in R2 with respect to the basis B. And so we can think of this linear transformation not in our original R2s that we're writing with respect to the standard basis, but with R2s that we're writing with respect to the B basis. And in this case, the transformation that we have there is given by this matrix that we're calling T simply, or the B matrix for the transformation T. And so how do we get that? It's the same way we get the matrix of any linear transformation. We take the basis vectors in order, and each column of this is where it sends that standard basis vector. So the basis for this space is B1 and B2, so what does this do to B1? And what does this do to B2? And since we already know what these things are in terms of the basis, then it's easy to write these things down. So T of B1 is just B1. B1 with respect to the basis B is just 1, 0. That's just saying, what is this element? It is 1 times B1 plus 0 times B2. It's just B1. This one, we're saying, what does it do to B2? It replaces it with negative B2. And how do you write B2 with respect to that basis? It's 0 times the first element plus negative 1 times the second element. So that's one way of getting this. Now, can you remind me what the questions were that it was asking? What does it do to...
Yeah, so we've got the B coordinates of T of negative 1, 2 are negative 1, 2.
Yeah, that was the second part that you were asking about, right? Well, that's just this column right here. I think the way you were proceeding was you were looking at, let me think about this. So we want to know T of B2 with respect to the basis B. I shouldn't write B2. Let's write the same thing that you're writing, which was negative 1, 2. So this is what you're looking for, right? that if we look at this, so the change of basis vector b for b times this should be equal to t of negative 1, 2. Right? And so what you were doing was solving the augmented matrix, or reducing the augmented matrix. So PB is just the two basis vectors. PB, this is 2, 1, minus 1, 2. That's the thing we're trying to figure out. And then we need to figure out what the transformation does to this element. And like I said, these two basis elements were picked so that it's easy to see what the transformation does to them. So there should be 1 minus 2. We pick one of them to be on the line and one of them to be perpendicular to the line. So when you flip it across the line, it's negative. So the system is 2, 1, minus 1, 2, 1, minus 2. And we could solve this, but the solution is obvious, right? Because this is an invertible matrix right here. It's going to have a unique solution. There is going to be a solution, and it's going to be unique. And so we can see that this is just the negative of this. And so when we reduce it, we should get the answer. Maybe we can reduce it. So I'll take this row, multiply by negative 1/2 this one, 2 minus 1, 0. So this becomes 1/2, 3/2, and then minus 1/2. Minus 5/2. So multiply through by 2/3. Minus 5. Doesn't seem right. Did I do something wrong? Probably.
The 3 house should be 5 houses as well, the positive.
Oh, yeah, you got it. Okay, so this should be 1 minus 1. Oh, now it becomes easy. So 2, 0, 2, 0, 1, minus 1. And I don't know why I'm writing all this out. 0, 1, minus 1. Did I do this one? Yep. You saw it. I'm sure you saw it. Okay. The better you get at math, the worse you get at arithmetic. That's the old saying. Okay. So anyway, there were a lot of ways to approach that part of the problem. But the most straightforward way is to say, in the basis B2, the transformation turns this thing into its negative. In the basis B2, this is 0, 1. So in the basis B2, its negative should be 0, negative 1. And this is the part I was talking about. Now, does that answer your question? Okay, then I should stop and move on to another question. I'll leave that for a second. This no one needs. This one no one needed to see this. All right, what should we talk about? Today's a review day, which means you're the boss. What do you want to know? Let me get the simple questions out of the way. The exam will be about the same length as the exam one. It'll cover everything up to Graham-Schmidt. Well, the Graham-Schmidt, basically, you're just going to need to find something that's orthogonal to a certain set of vectors. So you'll have a vector, you want to find another one that's orthogonal to the, not technically the Graham-Schmidt process, but you could use it to get it. I don't remember what we covered on the last exam, but this exam will be from there on. And with a little bit of like, you need to know the other stuff. You need to know the earlier stuff in order to do the problems, just like usual. No bonus questions. What did you want? Basically like exam one. Exam two is a little different because I put some extra stuff on there and the bonus question. So. Yes.
For finding the eigenvalue question, can we like, will it be probably like a 2-degree polynomial instead of like a nasty?
Could be. I don't remember. I printed the exam out last night, but I don't remember what's on it. So let's look at an example. The answer is, well, the answer is I don't know, but the real answer should be you don't know. You should be able to do a three-dimensional one. So let's do a three-dimensional one. Let me have a taste of my own medicine. Blah, blah, blah. Yeah, maybe we'll do that. So let's do this one. Cherry picking one that looks easy. Because I'm a coward. Number 14. Okay, so here's the matrix. 5, 0, 6, 2, 1, 7. I'm going column wise. For anyone who can't read what I'm writing. 3, 0, minus 2. It's number 14 in section 5.3 of the book. So if this is A, let's say let's do the whole thing. I'll figure out what the eigenvalues are. I might regret this, the eigenvectors too. More accurately, the eigenspaces associated with each of the eigenvectors. So this is a 3x3 matrix. We will have up to multiplicity and up to the possibility of complex roots, or complex eigenvalues. 3 eigenvalues. So let's take a look at this. So how do we get that? We first form the matrix A minus lambda I. Writing out all the steps, it's not necessary to write out all the steps. Now, having said that, if on the exam you get the question wrong, it would be helpful if you wrote out the steps because I'll see how much part you read. 3, 0, minus 2 minus lambda. Okay? And then we get the determinant of this thing, and that gives us the characteristic polynomial, the roots of the characteristic polynomial. And you know where I'm going with that. Okay. Now, this is sort of in line with Andrew's question. How am I going to compute, how am I going to figure out what the characteristic polynomial of this is? I take the determinant, I do cofactor expansion, just like we normally do. But I'm going to pick the easiest row or column, and that is this one. Right there. Oh, you know what? Just remembered something. I had nice chalk today. A little nub, but you know, I'm going with it. So this will be the easiest one if I do my plus minus thing, I want to remind myself that I'm not screwing this up. There's the plus, the zeros of course don't matter. So the determinant of A minus lambda I will be equal to this thing times the determinant I get by eliminating this row and this column. So that is 5 minus lambda times negative 2 minus lambda minus 18. Something I can't remember if I mentioned this or not, but computing the characteristic polynomial is a little bit forgiving of getting signs wrong. If I put a negative out here in front instead of a positive, wouldn't have mattered. The roots will be the same. So that's good. Now, first thing we notice right off the bat, this polynomial is already partially factored. I've already factored out, this is 1 minus lambda times some quadratic, right? This was a cubic, but because of my very clever choice of how to do the cofactor expansion, I've reduced the amount of work I have to do by a little bit. Now I've already got one of the factors, and I just have to factor a quadratic. So I'm going to say lambda equals 1, and then the rest is to be continued. So I'm only going to work with what's left. If I expand this out, I get minus 10, so plus 2 lambda, minus 5 lambda, plus lambda squared, minus 18. Double checking. And then gathering like terms, I get lambda squared minus 3 lambda, and the book, just being polite to me, this will be something that's easily factorable. So how do you factor 28? 4 and 7? Right off the bat, the difference is 3. So this is lambda, I need more negatives than positives. So lambda minus 7 and plus 3. So my eigenvalues will be.
Shouldn't be plus 4.
Yes? Yes, it should. Absolutely right. I'm embarrassed, but I still appreciate it. Now let's see if I can get this right. 7. Okay, so now that we've got that, we can go to the phase of, well, these are our eigenvalues. They're all distinct. We had no multiplicity we had no multiplicity greater than 1. All of them are distinct, and that's all 3 of them. So we can say right off the bat something about this matrix. A is A is diagonalizable. Whenever you have an eigenvalue, you can say something about the associated eigenspace's dimension. The associated eigenspace's dimension will always be at least 1, and it can be as high as the multiplicity of the eigenvalue. So there's a multiplicity of 1, 1, and 1. So each of them is going to have, each of the associated eigenspaces is going to have a dimension at least 1. That's 1, 2, 3. That adds up to 3. And so we will be able to get a basis out of the eigenvectors. There will be a basis for our 3. So So let's do that. Let's actually, just finish this off. How do we get the eigenvectors? How do we get eigenvectors? Right? An eigenvector is a basis for the eigenspace. So our choice is only unique up to multiplying by some scalar. Right? If we multiply by a scalar, we still get the same eigenspace, as long as the scalar is not 0. So oftentimes what people will do to eliminate that possibility of a choice is to insist on unit eigenvectors. We're not going to make that assumption because it just is more work for us. Okay, lambda equals 1. We'll start off with that one. So a minus 1 times I, 4, 0, 6, minus 2, 0, 7, 3, 0, minus 2. Yeah. And so now we can do our row operations in order to get what this should equal.
Would the bottom right one not be -3?
Very good. Well done. This is not going well. I take that back. This is going great. Okay, so what do I want to do? I want to start doing row operations. Now, if I were solving this like an ordinary system of equations, I would do the augmented matrix like this. But we're trying to find the null space of A minus I. And we would tack on this additional, the solution vector. But since it's zeros, we don't need to write all that out. It's not going to change in the process of doing row operations. So I could just do row operations. I don't have to do it in the exact row reduction algorithm. I could just do it in a way that's easiest. So let's do it the regular way. Take this, and I'm going to multiply it by -3/2. So that I get 4 minus 2, 3, 0, 3, okay, plus 7, so 2, and then -9/2 plus -6/2 is -15/2. So now I'm going to divide this row by 5, so that I get something I can use to cancel out here. 4 minus 3. I don't know if my thought process in all this is actually all that helpful because you've done this many more times than I have in this semester. There's 3/2. Actually, what do I want to do? Yeah, I want to eliminate this one. So add this to this. I get 4, 0, 3, 0, 0, 0, 0, 2, 3. Yeah? Okay. So we have 4x1 equals 3/2. 2x3 equals minus 3/2. And of course x2 equals x2. Doesn't matter what x2 is. No. What am I saying?
think you're missing like the X three would be with the three halves, and then like signs and such, because you have to add the zero. Like it'd be 4x1 plus 3 halves equals 0.
You are absolutely right. 4x1 plus 3 halves times 3. And, 3x. So we get, x1 equals minus 3, and x3, x2 equals 3/4, x3, and x2 is 3. So the, associated eigenvector will be minus 3/8, 3/4. Okay, so next is 7. Oh, should I really go through all the work of this? You know how to do it? Maybe I'll do it again and not screw it up. Give it a shot. Should go quicker this time.